Okay, folks. So, as always, first thing you do, you read the question very carefully and you look at the number of marks, thinking you have about 90 seconds per mark. That is about 3 minutes for this question. All right, everything, of course, goes back to that initial question because this is A through F. So here we have a 10 centimeter cube sample of the sodium hydroxide solution, the one that you just made, was titrated with zero point 0.2 moles per decimeter cube solution of hydrochloric acid. Now, this is actually an easy problem, but I find that students frequently get mixed up with this, okay? So what we're going to do is I'm going to try to make this clear for you. This is a titration, okay? So you're taking a chemical and you're putting it into another chemical. Was titrated with. So if we're using this picture right here, it says a 10 centimeter cubed sample of the sodium hydroxide. This is being very frustrating for me, so there we go. A 10 centimeter cube sample of the sodium hydroxide solution. Okay, so that 10 centimeter cube sample, that would be what is in the beaker. Okay, so this is your 10 centimeter cubed sodium hydroxide. And I'm going to color code that as blue. All right, was titrated with a zero point 0.2 mole per decimeter cube solution of hydrochloric acid. That I'm going to color code as pink, and that would be what is in the burette. So this is a 0.200 mole per decimeter cubed hydrochloric acid, and that would be in the burette. Okay, and again, I'm going to color code that as pink. All right. Now, what underlies all of this is your understanding of what happens when you put these two things together. So when you put these two things together, you're going to have sodium hydroxide is going to react with hydrochloric acid, it is going to make water, and it is going to make salt. That is a balanced equation. So that means that this is a 1-to-1 ratio. And what that means for you is that the number of moles of hydrochloric acid is going to be equal to the number of moles of sodium hydroxide. Now, because of that, what we need to do is we need to figure out how much hydrochloric acid was required, because we know the concentration. So, down here, we're basically asking ourselves first, what is the number of decimeters cubed of hydrochloric acid? Okay, so that's the first thing. Then we can figure out the concentration of the sodium hydroxide. Now that is a very long-winded way to go about this, but what I find is that students, the math is not a problem, it's the understanding what it is you're doing. Now, to help you follow this along, I am going to color code these burettes pink, just to remind you that this is the hydrochloric acid. Okay? All right, now let's get to the actual rest of the problem. So what are we trying to do? We're trying to determine the actual concentration of the sodium hydroxide solution for this titration trial, record the initial and final volume in the data table to the correct number of significant figures. So there's actually quite a lot going on here for a pretty small question. All right, now it says NaOH trial. That is true, okay, but don't lose track of the idea that these things here are actually hydrochloric acid. Okay? Because if you lose track of that, then the whole thing stops making sense. Okay? So first, what's our initial volume? Well, the initial volume is here. Clearly that's 10, that's 11, that must be 10.5, so that must be 10.1, that must be 10.2, we're between them, so that must be 10.15 centimeters cubed. All right, so we're going to put that in there, 10.15 centimeters cubed. Final volume, 22, 23, 22.5, that must be 22.6. Now, be careful here because it's 22.6, yes, but this requires 2 decimal places. Because if it was more than 22.6, it'd be 22.65. If it was less, it would be 22.55. So you have to put that 0 in there. Now, the volume that got used is just the difference between those, right? Because you fill up your burette to say here, you run it into the beaker, it falls to say there, and then that difference right there, that is the volume that was used. All right, so the volume that's used, we subtract those two, and that turns out to be 12.45 centimeters cubed. And remember, all of that, every bit of that, that is hydrochloric acid. So the first thing that we've got to do is we've got to find the number of moles of hydrochloric acid. Now, remember your equations, moles is equal to concentration times volume. And volume, of course, has to be in decimeters cubed. So that guy right there has to be in decimeters cubed. Divide it by 1,000, or simply move the decimal 3 places. And you have 0.01245 decimeters cubed hydrochloric acid. So we're going to go ahead and do that calculation right here. So the number of moles of hydrochloric acid is equal to the concentration of hydrochloric acid, which, if you recall, was the 0.2000. 0.2000 moles per decimeter cubed times 0.01245 decimeters cubed. Those will cancel each other out, of course. We end up with moles. So 0.2 times 0.01245 is equal to 0.00249, and there's actually another 0 there. And the reason for that is that this has 4 significant figures. Remember, the first 0 is insignificant because it's before the decimal point. So if you were to take this and put it in scientific notation, you would move that decimal 1 place, and it would be 2.000 times 10 to the negative 1, and then those are your significant figures, and so that's 4 significant figures. Then, of course, this was 4 significant figures, and so because of that, this has to be 4 significant figures. 1, 2, 3, 4. So you have to have that 0. These zeros here are not significant. If you wrote it as scientific notation, it will be 1, 2, 3, 2.490 times 10 to the negative 3. All right, so a little sidetrack, little side quest for significant figures. All right, so that is moles of hydrochloric acid, but that is also equal to moles of sodium hydroxide, because, as we said, it is a 1-to-1 correlation. Now, we need to get the concentration for sodium hydroxide, which is what the whole purpose is. Now, if moles is equal to concentration times volume, then concentration must be equal to moles divided by volume. So we're going to take the concentration of sodium hydroxide, it's going to be equal to the number of moles, which we just calculated there, 0.002490 moles sodium hydroxide. Then we're going to divide it by the volume of sodium hydroxide. Now, just in case you've lost track, it was a 10 centimeter cube sample. Well, again, we're going to put it in decimeters cubed, so it is 0.01000 decimeters cubed sodium hydroxide. Ooh, don't want to do that. 0.01, right? 0.01000 decimeters cubed sodium hydroxide. Now, when I do that calculation, divide by 0.01, I get 0.249. Now, they said correct number of significant figures, right? So, this is where they're going to get you if you're not paying attention. There is a 0 there. And the reason is that had 4 sig figs, that had 4 sig figs, so this has 4 sig figs, right? This guy here has 1, 2, 3, 4 sig figs. So everything in this calculation has got 4 sig figs. So that means the answer needs to have 4 sig figs. Since that 0 doesn't count, we need another significant figure. That has to be 0. Then we take our units, moles per decimeter cubed, because it's concentration, and there we are. And it's always good to tell the examiner, this is what I think the final answer is. Okay, now that was a long way around the houses for that particular problem, but there's a lot of stuff going on there. So let's check and see how we did. Let's look at the mark scheme. All right, so 10.15, 22.60, 12.45. Okay, that was fine. That's exactly what we did. Then this calculation is the 12.45 centimeters cubed, right, times the divided by the concentration of, or by the volume of the sodium hydroxide. Now, it looks a little different from ours because they kept everything in centimeters cubed, simply because those two things will cancel out. Personally, I do not suggest that students do that. I suggest that students always work in decimeters cubed, simply because that is the definition of concentration, is moles per decimeter cubed. But anyway, all of the penalties are there. Now, just notice when you're talking about the IB, they often have these notes to the examiners. Do not award this mark without all 3 values containing the correct significant figures. That's to catch people who don't write that as 22.6. Do not penalize M2, that's this mark, for significant figures. And the reason for that, of course, is it says data table to the correct number of significant figures. And then it also says ECF error carried forward. So if you did this incorrectly, but then you did the calculation right, you would get this particular mark.